So as you hopefully know, you have a strike slip homework is due Thursday right before class. I pushed back the deadline a bit, so we will discuss it in class, so no extensions. So please get it in on time. I had office hours yesterday, which I had 2 people come. I was hoping for a few more. We had a good 2 people that were here. We had a good discussion, and I hope that they learned a few things. But for everyone else, if you are going to come to class and say that homework is hard and challenging, then it's really important that you then come to office hours, because that's a time for you to discuss these ideas with me and Rachel, to get fairly personalized feedback and ultimately help you get better at these new mapping skills, which I agree is difficult, but please take advantage of these opportunities and come to office hours. I can almost guarantee you either you'll do better on the homework or it'll take you much less time to get the same score, or probably both. So Rachel has been very kind and is offering a second office hour, which I just put in the Zoom or in the chat link. And so those are tomorrow, 9 to 10 Mountain Time, and that's the Zoom link. So again, please take advantage of these to further improve your mapping skills. So today, we're going to do a few items. First, going to have Rachel discuss the GIR for Kumamoto. It'll take maybe 10 minutes or so. And then we'll move on to Ramon's lecture on strike slip faults. And please ask questions to him about questions you had in the reading or just anything else that comes up. And then if there's any time left, you can ask Rachel questions about the homework, or if not, then the extra office hours tomorrow. Are there any questions? All right, Rachel. Let me make sure. Yeah, I can share a screen.
So I'm going to try and do these a little bit when we have extra time in class to kind of show you how to apply the GIR in different environments. Kumamoto is going to be an example where there's heavy modification by urbanization, vegetation. So I'm going to show you guys what the GIR might look like when you're trying to identify some of these features in an area where they're not very apparent at all. So this, I have a little section of Kumamoto right here, and there's a rendered hillshade. And you could kind of see, and I'll zoom in a little bit. That is heavily modified by urbanization. I'll point them out here. There's a river right here. The whole area has been, pretty much the whole area has been modified for farming. You can see the outline of these terraces right here. There's some roads and a river that's been cut out through the whole system. So when you first look at this area, it's going to be a little bit daunting to try and see any clear indication of faulting in this area, because a lot of it might look like faulting, but it could also just be a result of the urbanization on the area. And so what I like to do when I first map this kind of environment is to mark out all of the anthropogenic alteration. And you can do it multiple ways. Like if you want to put a bunch of alteration points everywhere, you can. But I kind of know that there's just going to be giant swaths of area that are going to be hard for me to kind of analyze more detail where faulting may occur. But I could, after more inspection, pick out this kind of central zone where the vegetation occurs and kind of cuts off some of the terraces where faulting may occur. But it also seemed to have the more like clear features. There wasn't as much erosion or anthropogenic alteration in that area. And I marked out with AA where all it could be, and then this PAW is the proximity to active water where the river has been cut out. And it's okay also, like when you have an area like this, that there aren't going to be that many features. You may just have one feature that has a high ranking, or it just might be like a bunch of modifiers to indicate faulting. So when you get into the main mapping assignments, it's okay to not have a lot of features, and it might just be like one or two things that indicate a fault because it is so heavily modified. But I started clicking out mostly the modifiers to see if I could locate the fault. And you can see here I have like alignment or something like a morphologic element. Something I did to try and suss out the location were to take a bunch of profiles along the terraces going perpendicular, because they will like most of the time be oriented in a way where they're similar terraces of one elevation and then it goes down to the next one. So if I were to take profiles across the area and look at the elevation change, if there's any kind of unnatural disruption of the elevation, I could see kind of like a slope break of a morphologic element, or if it was distinct enough and I had other features surrounding it, I could also identify it as a scarp.
You have a question about maybe doing a quick profile demonstration, Rachel?
Yeah. And this will actually be something that you guys will implement on the next homework assignment. So it will be, and there's instructions on it too when we release it, but it's a plugin that you have to get from the Python plugin. So it'll be up here when you have it on the toolbar, and then you'll have to search in for the Python plugin. But when you do have it installed correctly, it'll be this button right here, the terrain tool. And when you click it, it pops up this profile tool. When you hit add layer, you have to make sure that the layer that is being added is the original DTM or DSM or DEM, just the one that contains all the elevation data. If you do it on the hillshade, it'll look like super obscure. So if I show you an example, like this is the hillshade. So if I were to add this layer and take a profile across this point, it's going to look pretty hanky. But if I do it on the normal hillshade and I have that on arc instead of this, but then you'll be able to see a more like smooth profile. And in the example too, in the homework instructions, you'll see what it looks like. If you want to try identify a scarp, you'll see it kind of smoothly. There might be a little divot where a slope break might be from a scarp. But yeah, you just have to make sure you have the elevation data and put it as a layer. And I like to draw like just a bunch of lines everywhere to see. And if they follow along the same strike of where I think the fault may be located and all of the like slope breaks line up, then that could be a good indication to help you try and suss out the location.
Let me just add a couple quick things there. So as I said in the chat, you want to use both the digital terrain model and the digital surface model. So this is the DSM, which has all of the points, which is why there's a lot of vegetation shown. It's dense, and so sometimes it's, can be helpful, but you see a lot of the veg and you see a lot of structures. So the DTM would be a DEM produced from only what we think are the ground returns. And that one in this case can be sparse and have some artifacts. So it's important to look at both. The other thing I wanted to add is just down below that ridge that Rachel's working on, you see another scarp kind of around here, but these are these sort of scalloped forms, and they're right next to an active, although now sort of modified anthropogenically, river channel. And so that's why you probably wouldn't necessarily suspect that much active faulting along that side of the ridge, whereas the other side doesn't have that bounding active channel. And of course, you have to think also about the setting. So, okay, now Japan is well settled and heavy anthropogenic modification is likely, but even just 100 years ago, this would have been a much more rural and agriculturally dominated environment with much less mechanized modification. So we're just really having to see through that sort of 20th century or so of heavy modification.
Yes, exactly. And there are cases too where the fault trace could be like exactly right next to the road or exactly up into some of the urbanization. So you'll have to try and look on either side of the most heavily modified to try and find areas where the GIR features may be a little bit more distinct and try and use that to find the strike of the fault and cut it across, because it's going to take some time to, it won't be immediately apparent that where the fault is located with all of the anthropogenic alteration going on. So it just kind of takes like a little bit more time to suss it out as opposed to somewhere like Wallace Creek where it's like very highly preserved. But I also used like little things like vegetation lineament. And when you are using the GIR and you're mapping it, you can like use these points just to place them down. If you see a vegetation lineament, it may not necessarily be a result of faulting, but if you do place it everywhere you see it, then you can determine like later on when you're trying to do your analysis whether or not it is a result of faulting to help you locate the fault.
A quick question from Isabella. The question is, do we always map the fault as continuous even if we don't see any GIR features along strike? And I'm about to write, it's okay for it to be discontinuous, but sometimes there's ridges or scarps that help you have a sense of the continuity of the feature. But I like discontinuous faults. A lot of other styles of mapping will have more continuous ones. I think it's a little bit of scale dependent, where if you're far out, you'll see it as a more continuous feature, but as you zoom in, you'll end up breaking it. So you just have to try to be consistent however you do that, but also look for supporting information.
Right.
Or talk a little bit later about primary and secondary faults and how to draw them as continuous or not. And another piece of advice is to think about what the fault is doing at depth. So do you think it's at continuous few hundred meters below the surface? In that case, does it make sense to draw continuous at the surface? So we'll discuss some of these ideas later.
Mm-hmm. Exactly. Because if you think there is like one large main primary fault in the area, you'd likely want that to be more continuous than your primary strands that may or may not match up or be continuous. So it's kind of up to you guys to like make a qualitative judgment if you'd like it to be continuous or not. Or sometimes they like you have it like kind of wrapping around a lot and it doesn't maybe look that natural. So you do want to go ahead and like break it up into smaller discontinuous traces. But this is pretty much just like, this was it. I just wanted to show an example of something where there's an environment that's not going to be as clear and there won't be that many features to draw from, but just some of the tools that you can use in an area that's going to be more modified, includes more vegetation and more erosion than another more preserved area.
Yeah, and I'll just add, this is demonstrating the GIR, but don't forget about the other things you guys have been learning, other tools in your tool belt, and that's the morphologic mapping. So when you're at a loss, just start mapping the morphologic features so you'll know, okay, well, this is the ridge, this is a scarp, this is the active channel. And then also even here, the mapping you're doing for the Landers case is for the desert, but even here I can see this boundary of the valley here is probably some kind of a Holocene surface, like a terrace. It's inactive in the sense that the channel's now channelized, but it's still an area that's fairly smooth and I would suspect is fairly young. Other things you can watch for and be suspicious that these little scallops, as I mentioned, might have little landslides in them. It's quite common that we would see that, maybe lateral erosion from the channel or something would drive these little slides out. So, I feel, and I've been trying to say this every time, that the morphologic mapping, the GIR, and the surficial geologic mapping are all just means to an end. They're means to help you look over the mapping area and look for suspicious features to kind of guide your eye. So, this is a very difficult assignment to map at Kumamoto because the slip rate's relatively low and the surface process rates are relatively high. So it's totally a detective project, but you just have to be patient with yourself and use some of these tools to help you kind of look around. And then I think suddenly things will start to pop out.
Yeah, good point. When in doubt, just like go back to what you know, map the morphology. And I'll show more examples too when we have like an extra 10 minutes in class of different kind of environments to show the different appearances some of the GIR features can have depending on the faulting environment, and then like also the location of the faulting area.
And this just looks like you have a seam here between two hillshades with different illumination directions, I think is what that boundary is. So be caught. So just explain that, but also people should be cautious as structures.
Right. I think, yeah, it cut off a little bit, so I created another one with the data right there.
Could you go over what the SSOSP and all those acronyms are?
For like just the ones on the assignment, or like what they are in general?
Just like what they are for this example, because I don't know them.
So the ME is going to be the morphologic element. So I kind of use that more as like a general slope break if I didn't have like enough evidence to identify it as a scarp, if it was too close to a farming terrace or something. But then when I got closer to my areas of higher confidence and I would draw my profile tools and try and locate it, the QSP would be a scarp and a quaternary deposit. And then the prefixes before just SS, R, or N indicating the type of faulting environment it is. And this is kind of a feature of like a lower ranking, and I don't necessarily know if it's accurate or not, but I put it as a bench because where I had my trace more towards the left side of the screen, if it were to continue along strike, it would be where this weak primary fault is traced. But if it were to follow more closely to the range front, it would be right here. So I did have this kind of like bounding area of higher elevation to either draw along the range front where the terraces are or bring it back up to the vegetation lineament. And that's okay if you do want to, if you think it splays a little bit in that area, you can draw two traces if you like. And then I have the anthropogenic alteration. And again, if you guys think it's more helpful to make a bunch of anthropogenic alterations to try and cover the extent of it, that's fine too. And then I have some, and I don't know if you can see it with the vegetation, but I have some vegetation lineament. And then I also use some alignment modifiers. If all of my features of low like ranking or modifiers followed along the same strike, I might put an alignment to show that there were multiple of the same feature along a certain length, which I think in the student GIR table, it says it has to be like less than a kilometer or something, that all the features have to be repeated.
Oh,
And you have,
no, go ahead.
oh, you have anthropogenic modification not on faults, and you said last time to only use them along faults.
Yeah, I put them just for simplicity, like in the middle of like the kind of blocks of anthropogenic alteration, but you know that like it would extend all the way up to this terrace. So it can help if you want to put it like closer to where the fault could be. If you want to put more than one, because it is such a large area of urbanization, you could put a couple here to kind of maybe put points to the bounds of the alteration. or you could just put one in the center and just use your like geologic interpretation later, or just know that the alteration like pretty clearly goes up into my fault trace.
We had a question also, Rachel from OB, about why that morphologic element is not a scarp, because it's kind of a scarp. But so, you know, what it was in your mind, is it because it's sort of irregular in profile, or what?
This one,
Yeah.
yeah. When I drew the line across, it didn't have the same, like the same size of slope break as the other profile measurements I drew across to identify it as a scarp. So it was like less so. So that might just be due to erosion. And that's why it might have covered up the evidence a little bit of it. But it's also really close to this active and maybe human induced water channel. And so that kind of lowers my confidence whether or not that, and it's more like linear, that break right there is due to it being a scarp along the fault trace, or the fact that the landscape was just carved out to that point to account for the active water channel and the terraces. Whereas like this one is a bit more natural on the range, on the, not the range front, but like the front of the hill slope. And then again, with like the profile tool, the break and slope, the size of it matched up more cleanly over here than it did where I have it in the south.
Yeah, those are good questions. And I think it shows, you know, that it's like we have these words of the GIR, these different elements or components, and we're still looking at how best to use them. But I thought that was a good answer. You know, so it's kind of degree of scarpness. If it's too weak, then defaulting to a little bit more generic indicator like the morphologic element sounds reasonable. But again, as I keep saying, I think if people are just consistent, however you do it, and you do it internally consistently, we can certainly look at the performance of the GIR, and that will be great. And so, you know, they're like much mapping, there's not always an exactly right answer. There's different ways to solve the problem. Okay, so what's up next then, Rachel? Did you have another item to present?
Just Kumamoto today, and then on Thursday I'll have some more examples outside of our main mapping project areas to show you guys.
Okay, and then so yeah, I'm just helping since Chelsea's a little bit busy there with David. So what I'll do next is do this lecture, kind of a generic lecture on strike slip faulting that hopefully will bring up some questions for you. But then we'll watch the time and save, you know, the last 10 or 15 minutes for questions that you may have on the homework. But also encouraging you guys very much to hit up the office hours. So are we okay? Yes, no, maybe so. All right.
Yep, all good.
Okay, let's go here. So strike slip faults are a pretty large topic, as I'm sure you can expect. So does this look like a PowerPoint about strike slip faults? Okay, so here, the idea that I had, that we had, was to talk a little bit about some basic ideas and definitions about strike slip faults. So kind of talk about standard model, and then discontinuous strike slip faults, because I think one of the things that does get in people's minds is awareness of the structural geology of the system. And all faults are discontinuous, but so when we talk about strike slip ones, a lot of the interesting activity happens where they're not straight or where they stop. And so we'll talk about that, and that's something that you kind of have in your head then when you're mapping a strike slip fault. And then we'll show some experimental examples to build intuition. And then I have some examples and anecdotes. So these are just to show maps and images of these fault zones to help maybe train your eye, see if you see something interesting. So we'll talk about San Andreas fault, and then the Alpine fault, and then a little bit from the Altentag fault if there's time. And I'll also show a little bit of landscape evolution modeling that's been done recently for strike slip systems that provide some interesting intuition as well. So in summary, the big things are kind of, like I said a little moment ago, it's the deformation rate relative to the surface process rate. So obviously, if you have a high slip rate and relatively low surface process rates, you're going to be able to see the fault structures well. So that's Wallace Creek. I mean, it's slipping so fast in a relatively dry environment without any real sedimentation that we see the story there spectacularly. Other places with low slip rates and high surface process rates, it's going to be a lot harder to see the structure. Localization is another question, kind of maybe it's consistent with the slip rate and the scale of mapping. So how discontinuous, how straight, how much is there just a single trace? These fault zone discontinuities, so steps and bends are important for strike slip faults. They produce a lot of vertical change, which is what really drives the development of the landscape. And then a big thing is what's the orientation of the fault zone relative to the drainage network? So if you remember for Wallace Creek, we have a beautiful, almost orthogonal relationship where the San Andreas is and the local slope of that alluvial fan are almost perpendicular. But in other cases, we'll have the river will be basically parallel to the fault, or the drainage network will be parallel, and so the kinds of landforms of development will be rather different. And then the degree of rock uplift along the fault zone. So if the entire zone is lifting, then the drainage network will incise and kind of be stuck. Whereas if you have obviously sedimentation, then you're kind of burying everything the whole time, and the fault is kind of continually rupturing through new material. And then also if you have differential uplift across the fault zone, you can develop a big scarp on the upthrown, on the upthrown side. So these are just a few quick thoughts that came to my mind as I was trying to summarize the presentation. So this is called the kind of standard model for strike slip faults. It's a famous diagram that shows basically depth as defined by temperature versus a number of different properties. And so what we tend to see is, like on the left here is the sort of rock materials. So we go from clay gouge to kind of frictionally generated melts and the formation of kind of pulverized material into mylanites. And that transitions about 300 degrees C. And then other things are kind of the frictional behavior of the fault zone. So this central diagram here, minus and plus, this is kind of unstable. That's where we expect the earthquakes. Whereas as we come to the surface, the superficial material is kind of more passive. It doesn't have the strength of the frictional properties to have an earthquake itself in the upper kilometer, upper 500 meters. It's just kind of passively along for the ride. Whereas at depth, we blast these ruptures at high rupture speed through the main brittle part of the fault zone, or we call the seismogenic layer. And then at the bottom, again, we punch into zones of mylanites where we slow down the rupture and have a more stable kind of slippage. So the question is kind of what happens at the very top. And part of that then is also we know the faults are not planar, and so they can have steps in both a long strike and down dip. And so that's what's shown on the left here, a map view, kind of a left step and a right lateral strikes at faults, kind of a releasing. Actually, this is a left step and right lateral fault. So this is a kind of restraining condition, but also down dip. So this is like the arrows, so the plus in the circle means arrows, that side's going away from us. And the circle with the dot in the middle is like the arrows coming toward us. So we know that these discontinuities along these faults are 3D. And so if you look on the right, it's kind of like the hood of a car tipped on its side, where it's not planar, but it has this big dent in it. And then it goes into a big step over. And so this will cause a lot of interesting surface displacements that we might see that are not even right along the fault zone, but right next to it, as material has to ride over that bump and be carried away. And so these discontinuities are central to a lot of research in faulting, but in our case, we just want to think about them as affecting the surface manifestation of the fault zone. So the other thing that happens is, as we come to the very top of the fault zone, we have these discontinuities, but we also get these kind of shear zones at the surface. And this is what I'm trying to show, is like the zoom to the very top of the fault. which is this passive material, this velocity strengthening material. We can go through some bumps and bends, but then we can either go into a narrow shear zone or into a belt of shearing. And this is what causes this is a lot of different things. It depends on kind of the overall geometry of the fault zone. It depends on the materials through which they're rupturing, if it's more, bedrock versus less consolidated material. But this is a useful kind of perspective, and it's this top of the fault zone that we're looking at when we're trying to map it. Oh, I got a chat. Let me see. Yes, that hood of the car is like a knuckle. It's sticking out. A material has to bump over it and basically that usually causes some kind of vertical displacements. Okay, so then just turning to a little bit of experimental work. This is classical work. This is from a textbook, but it's actually from the 1970s. It was a clay cake experiment where we had maybe 10 centimeters of clay over 2 pieces of plywood that had a slit. And so it's like the fault is underneath. And as we progressively shear those 2 pieces of plywood, we deform the overlying clay. And so early on, we get just sort of uniform shearing. And then as you get to like C into, we start to break and we have these en echelon faults that in this case are left lateral. And then over time, we have progressive linking and localization. So this is something you want to watch for, is that the faults will in general become less discontinuous with more slip. And those are the terms we want to look for, is this kind of linkage. And that might mean that we might shut down other parts of the fault zone, other traces, and just have a single primary trace that's the active one. I'm going to go a little bit further and then we'll have some questions. So the next thing, so just a couple definitions. This is structural geology, so I don't want to I'm expecting that you know these things, but I just want to remind you of them. And so, the steps and bends are where a lot of interesting things happen, as I've been saying. And so you can have a releasing bend, which will tend to produce subsidence along the fault zone, and interesting secondary structures, maybe some normal faults or oblique slip, normal faulting and strike slip. And then the restraining bend's the opposite. So we might expect to develop positive features, and there would be maybe some more reverse faulting. One of the key things I think is the scale of these features, which roughly scales to the first order horizontal with vertical. So if you have a 1 kilometer size feature horizontally, it's probably telling you about the upper kilometer of the fault zone. If you have something that's 10 kilometers wide, a step over, it's probably activating the entire upper 10 kilometers of the fault zone. So it's kind of a one-to-one. It's not always that way, but it's something to be aware of, is that horizontal versus depth extent of these features. You can assume they're square, at least to begin with, or circular, and then obviously become more complex. Let's look. Okay, so this is a video. I'm going to stop for 1 second and reshare just so I remember to click this. Okay, optimize for video clip. I can't choose that, but this is a video from our from University of Massachusetts, Professor Michelle Cook. Can you guys hear me still? Sorry, I had a freeze on that. Let me just introduce this and then I'll try to play it. So it's a short video from UMass. Michelle Cook and her team, they have a really beautiful experimental facility that's kind of like 30 years newer than those clay cake experiments, and they can do some really interesting physical modeling of fault zones that may again help with some intuition. So let's try to show this. Screen 2. And it has a little audio, but I don't know if I'm sharing the audio. It's just cool sound.
I think it's just you, Ramon.
Hold on, let's just check, make sure I share share sound. I don't want you guys to miss this. Sorry, I'm kind of spazzing a little bit with this, but I hadn't anticipated it. There, hopefully that's good.
Yep.
We're here at the Physical Modeling Lab at UMass Amherst. I'm here with Kevin Tenenbaum. So Kevin, can you tell me, what is physical modeling?
Well, physical modeling is a technique that we use to allow us to study natural processes that occur over time scales and length scales that we can't observe in any other way. So today we're going to be modeling a strike slip fault system. So we'll be growing our faults in a wet kaolin, and it's a wet clay, and it has the consistency of about Greek yogurt.
Okay, so you can grow faults in something that's the consistency of yogurt?
Yeah, so we can actually see little fractures and then slip along those fractures and create faults.
Do you want to tell us quick what this is, what we're standing
So
next
this
to?
is our deformation box, and so we grow our faults in this. We first pour the clay, and we can either pre-cut faults or not, and then we can displace the box, and that displacement will grow faults.
Okay, so one side of the box moves, and then you say, oh, there's a fault.
Sorry, I don't know why my computer keeps stopping.
And then you take this ruler and you measure it.
So not quite. We use these high-resolution digital cameras to record the entire process, and then we use particle image velocimetry to analyze displacements on the surface.
I edited this a bit from that cool intro to then just pick a few of their models out. So let's just watch this one. So this is basically the shear strain rate along the fault zone. So the redder it is, the higher the strain rate. And so you can see over time how the fault zone is kind of developing from, you know, these different stages and you know, kind of different thicknesses of the layer. Here's a band at the bottom that in the cut that they put. And so then they're looking at how these secondary structures are sort of developing naturally from that. And then this is just looking at kind of the slip rate at different places along the fault zone. And what's important to watch here is the effect of the evolving geometry on the slip rate. So basically some of these faults will shut down or pick up speed as it evolves. Here's another one with a little bit of convergence. So partitioning, so what that means there is that there was basically a through-going strike slip, and then the next to it would be a reverse fault, and it's kind of popping that little block up. So let's look at that for a second. Where did my, let's go back. Yeah, so this is common that we see it where we'd have the zone is converging. So like the San Andreas fault system is not, the fault orientation is not parallel to the plate vector of Pacific plate. There's a tiny bit of convergence, something like this, 15 degrees. And so we have the through-going fault zone, but then we see as they highlight up there, we get this little slip partitioning. So secondary structures popping out on the side. And here's another one, a little bit more severe convergence. And again, secondary structures are appearing. And then global slip partitioning, that would mean that it was really separating into two fault zones, even though at depth there's only one slit in the experiment. So I won't spend a lot of time more on this, but we'll of course have the website or the presentation available, and you could just look through their YouTube. It's really wonderful, kind of mesmerizing, and then there's some really nice papers that they've published. So let's just do a little bit more structure.
Oh, Ramon, there
So
was a question in the chat that was, is the 1-to-1 ratio that you were talking about between length on the surface versus depth more of a rule of thumb or an empirical basis?
It's mostly a rule of thumb, but you can prove it to yourself if you do, for example, elastic dislocation modeling. You can kind of assume the Earth is an elastic half space, and you could put a slit in the half space, and the deeper you have the slit go, the broader the effect is. And you can do this both in terms of the buried tip and the size of the patch. So it can be explored, but it's mostly just a rule of thumb.
It also approximately applies to these sketches as well. So.
Yeah, exactly. So here's the 3D of some of these step overs where we kind of see that, you know, at depth, there's a single through-going trace, but they splay up dip in both the kind of restraining and opening examples, and it's also splaying along strike. So of course the Earth is more complicated than we want, but you get a little bit of sort of things to look for here. And then as Chelsea's pointing out, this width is, one is not so far different from the depth. So there's an implied rule of thumb, which is you can prove to yourself. There will of course be exceptions, but as a way of thinking, I think it's valuable. Okay, so let's look, let me just check here what.
These pictures are good to keep in mind of when you're mapping the surface and you see what's on the left here in gray, to then think about what is going on in the subsurface. So to keep in mind what you might map, thank you, Ramon, as the primary faults, and think that then this is really the fault that goes to depth and likely in the subsequent earthquakes is going to release the primary moment. And then you have these smaller secondary faults. And in this case, you see that they do connect to that main fault at depth. And the depth that they connect is quite close to the distance that they are along the surface from that main fault. So yeah, Ramon's writing red for primary. And so again, that's fault that goes to depth and releases the majority of the moment. And then in this case, we have these 3 or so secondary faults, much smaller, both along strike and their maximum depth. But yeah, just keep these pictures in mind when you're thinking about how to connect faults and how they relate to each other during earthquakes.
Yeah, and you might imagine, right, that from a PFDHA standpoint, the red faults is sort of a problem that the census didn't have probably the highest slip, but we might know where it is. Whereas the blue ones are trickier because they're lower slip. They might not have as much morphologic manifestation of prior motion, but they still could be annoying for a structure. So, it's important to start thinking about these issues. Okay. Thanks, Chelsea. That was very good to jump in there. Let's look another slide or two. Okay, so any other questions on structure? This is structural geology. If you're not familiar with it, hopefully you have taken structure at some point. Go back and flip through. This is our structural geology textbook we here at ASU because we have Steve Reynolds on our faculty, so we always point to him. But just flip through it and kind of put this in your mind as something that is part of that prior knowledge that ends up being useful for mappers. Okay, I'm going to push on then in the interest of time. So let's look a little bit at San Andreas. We've already been talking about the San Andreas some. We did the Wallace Creek exercise. We heard from Rich about northern San Andreas, so I'm not going to talk about too much. I will point you to this playlist where I made kind of I took hill shades from airborne laser scanning along the San Andreas, either Earthscope or B4 data, and I made little videos of flying along the San Andreas, all the way from Point Arena down to north of LA. And so they're on this playlist. You should check them out. I won't show them all now, but I will show a little bit from, this is just a small historical aside. This is a picture of the 1906 surface rupture from north of San Francisco. This is in the Point Reyes area. And so what you want to see, is have in your mind, this is a simple surface rupture tearing through turf, which is the grass, in 1906. And so you can see it's quite localized, but what's kind of cool to see is that there's a little bit of if you look at the profile here, there's a little bit of a bump there that looks like it's from more than just this earthquake. And so this thing here, this bench, it's kind of a flat area on the side of the hill, is probably showing us where there were prior earthquakes, and they probably looked like this one. So want to keep our eye out for it. This woman here, her name is Alice Eastwood. She's a famous botanist, and she was out here exploring with her friend G.K. Gilbert after 1906 earthquake. So let me just keep going. And that fault zone I'm showed on the right here, the same area. And what's important is also remember how I said at the beginning, when the drainage network is parallel to the fault zone, as it is here in this example, you get some very different looking patterns because you have to deal with that kind of collection of runoff that actually the fault zone is helping to localize along the fault zone. But then the interaction with the fluvial system is different than the orthogonal case like Wallace Creek. Okay, let's go forward a little bit more. So let's do one video. This is the creeping section, but it has a cool example. So we're starting south of San Francisco Bay Area. This is a digital terrain model. You can see the scarp right in downtown Hollister. You can walk there. People have their houses on it. So talk about PFDHA. This is where the Calaveras Fault splits from the San Andreas. So they're coming together and becoming the San Andreas Fault. This is an area with really beautiful small sag ponds. I'll talk about a little bit later. Along the San Andreas that's called Dry Lake Valley. And Chelsea published a paper recently from here, but you see this really nice kind of little troughs, which are those dark areas separated with a few little pop-ups, which are almost the same size, just inverted in which side's up. And then a kind of a more coherent scarp that develops. And then right above the ILL and hill shades, there's a sort of a deeper trough that is formed. Let's just look a little bit more at this part of the San Andreas. You see the value of the illumination from the perpendicular to the fault zone there. See some more traces. There's lots to look at, but this next place is called Mustang Ridge. And I'll show a little bit more about this in a moment. But here, again, we have the primary fault is basically bounding the shear zone on the southwestern side, and there's a number of splays that come off. You can also see sort of 2.5D here, the ridge. So the fault zone is actually a positive feature. And there was a famous quote from Clarence Allen from Caltech, who's a famous seismologist. He said, yeah, it seems like you always have to walk uphill to get to the San Andreas Fault. So for whatever reason, maybe there's a little bit of net extrusion along the fault zone or just coincidence, but there tends to be, it's not always low, it can be high. And that's the whole ridge, but then here we're also tearing the ridge apart by deformation. And so when we tip it on its side and look at it here, what we see is the primary fault is bounding that southwestern side, but there's a lot of secondary structures adjacent to it. So those we would want to keep track of. And what's pretty amazing here is actually, this is probably because the San Andreas isn't vertical. It's dipping up in this view, and this little block here that is Mustang Ridge is like a little flap that's deforming over the down dip San Andreas Fault. So this is a cross section here, and we're basically looking at this block above that's being sheared. So interesting 3D for this zone, and that's only known after a lot of mapping, but is something you want to keep in mind. But the main thing for our purposes would just be to appreciate where you thought the main trace was versus these secondary structures. Okay, I'm going to keep going. So here then is
maybe just discuss the geomorphology that you can see here that you would use to distinguish the primary from secondary.
Yeah, let me just jump to the unannotated version. So here, what I'm seeing, and again, first of all, get that illumination, get the sun in the right direction. So put the sun over here so we get some, shading that's going to help us. And then I see these scarps, here's a nice one, here's another nice one, another scarp here. This is kind of broken, this scarp here, a fairly straight but discontinuous complex of scarps. Here's probably, this is like a morphologic element of Rachel. It's a little uncertain what's going on right there. And actually I chose the wrong color for these guys because they're secondary. Let's quickly just do that again. So these guys would be blue as secondary features. We have a suggestion of something here. There is an interesting little pond right here. You see that sag? And so we'll talk a little bit more about sags in a few minutes. There's a few other closed depressions along here as well. There's some things up in here I'm suspicious of, you know, this alignment there. Another kind of closed depression up here. So this fault zone's really complicated. Probably take, you know, an hour to do a good job here to map it all. But then when we come to, you know, the sort of the big dog is the San Andreas, the main primary traces here, it's the concentration of GIR of indicators is quite a bit denser. But you can see, and then look at this, is kind of cool how it looks like it gets an echelon going through that little ridge. And again, remember, I'm throwing these lines down as the interpretation quickly because of the question from the group, whereas I would suggest that you start with the morphologic mapping, GIR and superficial mapping first before you do that interpretation. It's good, just good behavior. I'm misbehaving in the interest of expedience. The other quick thing you can see that this place is notorious for is these landslides here, this kind of and sort of a slide complex here that's basically eroding fluvially, but also failing by kind of deep-seated landsliding. There is a pond here, a closed depression, that when you first map it, you might be like, well, is that associated with the fault or is that associated with the landslide? And, you know, you have to build the story sort of piece by piece. You don't want to try to figure it all right at once. But with my experience in this area, again, here we see probably a coincidence of some of this fracturing that may be associated with the landsliding with the main San Andreas trace. And remember, our 3D view showed that this ridge, this Mustang Ridge, is higher. And so we might have deep-seated landsliding off of the side of that ridge. Any questions? Does the geomorphology change creeping versus locked? We wish we could tell. I think, you know, basically creeping, especially this San Andreas, you know, it's creeping at 35 millimeters per year. So these scarps are young, and in 100 years, it's 3.5 meters of creep. Whereas we haven't seen in like Carrizo Plain 3.5 meters to slip for 150 years. So at a detailed level, morphologically, I think you probably could argue that the creeping scarps, if they're localized, will be sharper in terms of their slope and curvature. But it's not been carefully examined. That's actually a great research question I keep trying to sell to students, but no one's bought it yet. So let me push on, guys, but hopefully that was helpful. Let's just go. So this is interesting. So we've seen this diagram a couple of times, but this paper we wrote was just a comparison of mapping, which is kind of like what you guys are doing. And so we compared three things. We compared Vetter and Wallace, how they map. So this is USGS scientists mapping in the field, but also with aerial photography. Stone and Aerosmith, this is me and a student mapping in the field. And then Zilke, he only mapped remotely. So he's doing what you guys did. And we picked a central San Andreas. So this is the same area on the San Andreas, 3 different repeats of the same hillshade, but with the different groups who are mapping. So you can see the top is USGS, Vetter, and Wallace, where they're kind of using the prototypical GIR, marking some things. They're just solid and dashed lines for their fault traces, pretty discontinuous, but also distributed. Whereas you can see in the middle is from purely field work with some poor quality aerial photography from the 1990s, so kind of pre-Google Earth. And there we were walking and we could see the main traces, but we didn't see much of the secondary traces. And the brown things are landslides. And then at the bottom is Olaf Zilke sitting with his earphones, listening to his music and just jamming line work through based on the kind of work that you guys have done. And he picked up the main traces as well, but he has some suspected secondary traces that he shows in blue. So something to think about. And then here was just kind of pointing out some of those same landforms, same morphologic elements or GIR features for this area with the high resolution topography. Now, there was a request to talk a little bit more about sag ponds. And so there's kind of a sensu stricto and sensu lato, which means, strictly speaking, we see them along strike slip faults, usually in structural depressions. From a broad sense, it's a depression along a fault zone. And so, which causes a closed depression, which accumulates water. But I'm going to show you kind of the more sensu stricto sag ponds right now. And this is a quote from above. I screen capped from the reading from McAlpin. And so here's a sag near Mustang Ridge. So you can see that green of that part of the Santa, that part of the Coast Ranges. Here's those pretty sags at Dry Lake Valley that I showed you guys a little bit ago. Very pretty, little tiny sags. Here's some more sags near in the Chelam section, and this middle area shows a bunch of saggy areas along the San Andreas. We trenched a bunch of them. One of the students, Alana Williams, did. You see a view of everyone smiling, but OSHA compliant in the trench. And here's one of those sags there. So you see the depression along the fault zone. These faults are really discontinuous here. Here's a view. This is again San Andreas and Chelam section. This is called Still Lake. This little sag right in the shadow there. This is two views of the same one. And again, you see that pretty straight trace of this plate boundary strike slip fault. Here's another sag on the San Andreas near Parkfield. This is a structural one, definitely. Can we find sags just symmetry? Yeah, you should see them either way. Like this sag here, we have topography, but because it's low, it has vegetation. Now, I'm going to jump to New Zealand. Everyone always says, oh, you only talk about the San Andreas Fault all the time. So let's look at New Zealand. New Zealand's famous for strike slip faults. The kind of two main groups are this part of the northern part of the South Island, which has this kind of splaying system in the area of Marlborough. There's also important faulting on the North Island, but then I guess the third important area is the Alpine Fault, which is the main plate boundary where things are pretty localized. So there's some nice work done by several groups I show here. First, this is a place where the faulting is pretty simple on the South Island, and you just see some nice superficial geologic mapping of these terraces that are progressively offset. So what you want to be noticing here is the different colors or different age fluvial terraces coming from the main active channel at the bottom. But look at the size difference of the offset of the riser. Basically, as the terrace gets older, the riser offset increases, which makes sense. But this is a classic story that was identified by Lenson in '68, but then revisited by Rob Zinke more recently. And the slides are from Rob. Let's look a little bit more. Sorry, next one. So here's another example. This is from Hayden et al., where there's the main fault traces coming through below. But then one important thing, and we had some discussion of this in prior lectures, is the Sackung. So it was German for sagging. And so what that often is that there are fractures that are on kind of positive topography near a fault. So it's probably associated also with strong ground motion, but it's not usually mapped as even a secondary structure. A lot of times the assumption is it doesn't link with the main fault at depth, but it still represents sometimes repeated zones of ground failure. So if you see them, you would want to map them, but you see they're short and they seem to be worried about the topography because they're gravity driven. Okay, clear. Were the mountains uplifted by the fault, or does the fault cross-cut pre-existing mountains? So you mean on the left side, the regional uplift, Ethan? Yeah, it's plate boundary zone, so the whole zone is lifting, and then it's being sheared by the fault. So it's sort of also two different time scales. The topography is built kind of at the million-year time scale, and these faults are sort of ripping through at sort of tens of 100,000-year time scale. Good question. Let's look at a couple more things, guys. I want to show you. Let me see. So So here, let's go the Alpine Fault. So this is where you definitely need LiDAR, because look at the veg here. I mean, this is like only day it's sunny probably in like once a year or once a decade. But this is also what they showed. So so you can see clearly the lower right is fully vegetated. So digital terrain models really help us. We can see actually a pretty good looking, fairly localized piece of strike slip faulting with also some ponding here. So you might suspect there's going to be a sag right there. So that's where it's pretty clean. But the next paper, this is from Barth et al. What they showed is scale matters. So when you stand back at this, 10 to the 6th length scale, so 1,000-kilometer length scale, it's pretty straight. But then as you start to zoom in, you see these big sort of segments that are kind of 4 or 5 kilometers long, sort of oblique slip. The whole thing is strike slip fault zone. But then at the bottom, we see this really discontinuous fault zone along the range front. And so, but that's at the kind of, fine scale of mapping. And so what they showed here was just that at depth, it's interpreted to be pretty simple, just the main fault. But then as you come to the surface and that scale, what controls that is a fairly interesting question, but it's kind of the upper kilometer, upper few hundred meters, we get this really interesting up-dip splaying. And also possibly because the material is a little bit less consolidated, we get a kind of a widening of the shear zone. I'm just going to keep going for a couple more minutes, Rachel, but I am watching the clock. Okay, so the last thing I really wanted to get to was this, which is interesting landscape evolution modeling that's been done in the last 5 or so years. And so here we take a simple model for landscape evolution. So it's simulating landscape processes in the computer, and basically it's solving this equation. And so the first 2 parts of it are the tectonic signal. So the U is rock uplift, and the VY DZDX is the shearing. And so it just kind of a question of how localized it is. That's why it has a DZDX there. Then this KA 1/2 S minus E crit, this is the fluvial part of the processes. And this is hill slope. So we solve this for everywhere in the model. And this would be tectonics. And this is a pretty standard kind of landscape evolution model now. But one of the main things that we see is it really shows us that when we have relatively low slip rate compared to the surface process rates, the landscape's kind of constantly readjusted, because it's like, oh, I can figure this out. That fault's not bothering me. But then once the fault slip rate goes way up, you can't stop it. It leaves its mark in the drainage network that's more persistent. And that's kind of the difference between the 0.5 and 20 millimeters a year. But let's look at a couple of videos that they provided. So this one is kind of same geomorphic conditions, but 0.5 millimeters a year. So we're going to look at increasing slip rate. And so here you can see the landscape's developing. It's just a narrow single fault zone, and the whole system's uplifting. So we have a pretty good incision-driven system. There's not much aggradation, which is one of my critiques of these models. But you see, it's developed a whole bunch of little offset channels. Now let's look at the next one, which is, sorry, let me see, what was the difference? 0.5. Okay, here's 1 millimeter a year, so faster slip rate. We're basically increasing the size of the offsets, but we're still kind of getting rid of them. There's some reorganization, drainage capture, and so forth. And then the last one, let me just make sure I have the right one here, is 20 millimeters a year, so it's ripping. And here it's going so fast, the landscape really can't forget about the fault. It has to deal with it. And so we see sort of more coherent disruption of the landscape along the fault zone. And so that's kind of what we're trying to say. It's easy to map when the fault's slipping fast, but if the fault slips slow, the drainage, the landscape can kind of erase the effect of the deformation. So let me see, I think I just had and so this is a kind of a summary of that, where they're showing ridges like marker ridges and ridge bifurcations. And in the slow slip rate, they're kind of constantly being reorganized. Whereas what you're supposed to take away from this is in the C case with high slip rate, it's actually fairly stable. And so the development of the morphologic indication of the fault zone is more strong with the high slip rate, which is of course what we expect, but this just explores it. So that's all I want to talk about, because I want to give a couple minutes to Rachel for questions on the homework. Yes, it's Land Lab. Thanks, Mindy. And we need to get going on this. This is a really interesting way of exploring some of these questions. So put this online, but I wanted to turn really quick just to save a couple minutes if people have questions about that homework. I can keep talking about strikes and faults forever, but let's turn just to ask any questions about landers?
I had a question for you, Ramon, if you don't mind, like explaining a bit more for the class, like when you identify a sag pond, whether or not it's confined by all boundaries of the feature when they're trying to identify it, as opposed to just like a depression, if it has to be sag like explicitly around all boundaries of the pond, or if it can lead into just like general topography at a lower elevation.
Well, it's a good question. I mean, you know, in a general sense, it's a closed depression and that it's near the fault zone. But when we find them, after you start to look for them, you'll tend to see that they're localized along the fault zone. So the closed depressions are developing either because of structural sagging, so there's like some transtension drops the middle down, or there's some kind of juxtaposition of topography. You know, if you have a channel and you shut it with the offset of a ridge next to it, you're going to kind of dam that channel and you'll develop a little closed depression right along the fault zone. So, you know, any one, just like all of the things we're doing, you know, any one of these features is kind of ambiguous. It's like, it's a closed depression. What does it mean? But if you start seeing a bunch of closed depressions that are kind of in a line, you might suspect that they're telling you something. And that's like the example I showed from Still Lake. It's just like boom, 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 boom. There's like 4 sag ponds right on the fault zone. And those are probably structural. So this very shallow, remember this one-to-one idea, it's just 20, 30 meters wide, 50 meters long, this little local transtension. And then next door, there's like a local pop-up that's, as I said, kind of the same size, just inverted in sense of rock motion vertically.
As a word of caution, so if you're looking in an agricultural area, of which many of the mapping areas are, farmers love sag ponds because water accumulates in them. So they'll often take advantage of them. They do also make other ponds that might be near the fault, but are not perhaps aligned with the fault. And so again, like roads, you should have just a little bit of more skepticism or be a little bit careful when you're doing this fault mapping to make sure that you're really mapping either a fault and not a road, or if you identify a sag pond, it's actually related to the faulting.
Yeah, and Aaron asked about if we would see gouge. We probably wouldn't. Usually you'd expect to just see sedimentation. But you know, sometimes you can have you know, the gouge has to form by more than, you know, just one earthquake. Usually is kind of more large amount of slip that's producing the gouge and pulverizing the rocks. And it might be a little bit more resistant rock